begin our journey into physics and digital signal processing, we're first going to talk about sound in general, specifically sound and air, and some properties of acoustics. Then we will talk about sound in computer systems, also called digital audio. Sound is changes in air pressure traveling through the air. Yes, of course there is sound in solids and liquids, but it usually needs to get into the air so that it can travel to our ears and we can hear it. So for our purposes now, we'll just be talking about sound in air. Sound propagates through the air, called traveling waves, as alternating compressions and anti-compressions of the air. Sound travels at a constant speed, usually labeled c in physics. This equation shows c, the speed of sound, as the square root of the ratio of E, the elasticity of air, and rho, the density. At normal air densities and humidities, the speed of sound, c, reduces to this expression, which is 331.4 meters per second plus 0.6 times the temperature in centigrade. All of this works out to about 343 meters per second or 1,130 feet per second in dry air at 70 degrees or so. The process of turning a sound in the air, which becomes a voltage at the output of a microphone, into a digital signal inside our computer, phone, or other digital system, is called analog to digital conversion. The conversion hardware is called an ADC, for analog to digital converter. In the analog to digital converter, first the voltage is sampled at regular intervals, called the sampling period, which is often denoted as T. I'm going to demo this right now with this sampling program. We've been seeing the waveform move across the screen, and if at any time I hit the space bar, it captures the waveform into a buffer, which we can then inspect. All right, so there's my waveform. Sampling consists of looking at this waveform at regular intervals in time, and we can see that the sampling period, the space between two samples, is called capital T. There are many things to think about when sampling. One is the rate. We can see that if there's lots of wiggles in the waveform, like on high frequency information, that we might miss some of the important information in the waveform because the samples aren't spaced close enough together. I can increase the sample rate, and we can see that by increasing it more and more, I capture more and more of the characteristics of the waveform. If we don't sample fast enough, we encounter a phenomenon called aliasing, where we can see that the space between the samples might give us the indication that there's some lower frequencies here than the frequencies that we're actually trying to sample. If we sample high enough, we can catch all of those wiggles. In general, it's required that we sample at least twice as fast as the highest frequency we expect to see in our original analog signal. Humans can hear up to about 20,000 cycles per second, also called 20,000 hertz, named after Heinrich Hertz. 20,000 samples per second is also called 20 kilohertz, which stands for thousands of hertz. So we would need to sample at least 40,000 times per second to capture the range of interest for music and high-quality recordings. In fact, CDs and MP3s usually sample at 44,100 hertz or 44.1 kilohertz. Other common audio formats, such as those used in audio for digital video equipment, digital and satellite TVs, etc., sample at 48 kilohertz. 48 kilohertz would give us a usable frequency range of 0 to 24 kilohertz. There are higher sample rates used in high-res audio, like DVD audio and super audio CDs, including 88.2 kilohertz, 96 kilohertz, and even 192 kilohertz. Telephone quality digital speech signals, however, are sampled at only 8 kilohertz, which is why telephones sound so bad and why we don't play music over the phone. You can hear that my consonants like s, f, t, and k are sort of hard to tell apart, But remarkably, we still managed to make sense out of phone conversations only with 4 kilohertz of total bandwidth. Once a waveform has been sampled, it must be quantized and turned into numbers. Quantization means that we can only store a limited number of different values in a given cell on a computer, often called a word. So we have to round each sampled value to the nearest available computer number that can fit in that word. We can see the effects of different quantization levels using our program. Right now, we're quantizing and we can see that the sample value has to be rounded to the nearest available quantum level that can be stored inside the word. We can increase quantization, however, and see that we get closer and closer to the actual value of the sample. If we keep increasing, we keep getting more and more accurate, but we take up more computer memory in the process. A common computer audio word size is 16 bits or 2 bytes for CD quality audio, which gives us a total of about 65,000 different amplitude values that can be represented in each 16-bit word. 24 bits is a common word size in higher quality formats and systems, and 8 bits is used in lower quality applications like speech systems. Quantizing introduces noise resulting from that rounding, and a rule of thumb is that each extra bit of word size represents about 6 dBs of quantization noise reduction. So 16 bits has about 96 dBs of signal to quantization noise ratio, but 8 bits would only have 48 dBs, and 24-bit word size would yield a whopping 144 dBs of signal to noise ratio. For reference, the dynamic range of human hearing from the quietest threshold of our hearing to the threshold of pain is only about 130 dBs. So 144 dBs spanning the range from the loudest sound to the noise floor, either due to ambient noise in the room or due to quantization rounding, is all we should ever need. Once a sound is sampled, quantized, and stored in our computer as a sound file, we can do really interesting things to and with it, other than just playing it back. The most popular formats and sound file types are WAV and AIFF, with the file extensions .wav and .aif or AIFF or AIFFC. MP3 files are a somewhat different thing because lots of work has been done to compress the samples so they don't take as much disk space or bandwidth for streaming. One of the great things we can do with sound files in our computer is to use a sound editor program to inspect different parts of the sound, which we will do very shortly. We can also edit and modify sound by using cut, copy, paste, and we can apply effects and do lots of other great things. The topic of this course is synthesis, but more generally, it's digital signal processing, or DSP. To hear more about DSP, we're actually now going to turn to our co-instructor, Julius O. Smith III. Julius was my thesis advisor at the Stanford Center for Computer Research in Music and Acoustics, and he still inspires and advises me to this day. Julius is one of the world's experts in digital filters, physical modeling, acoustics, computational acoustics, and many other things. Truly a guru of digital audio and DSP, here's Julius to tell us how important and pervasive DSP is in our lives.